Okay, so it's my privilege and more to the point, my pleasure to welcome Arul Lakshminarayan. Arul is a professor at IIT Madras. He did his PhD from Stony Brook, followed by a postdoc at PRL. And he's had distinguished visiting positions at Washington State University, Max Planck Institute in Dresden, and also IIT Kanpur. Arul is an expert in classical and quantum chaos, various aspects of entanglement, traditional as well as modern. And he's going to tell us today, I think, mostly about chaos, but also a little bit about entanglement. So, over to you, Arul.
Thank you very much, Sachin, and thank you for the invitation to this lovely place. My first time actually to the department, so I'm going to talk about Sachin. It's an hour, right? Oh, I have to be here. Okay, good. Don't say you're flexible to me, okay? It's a bad strategy. Yeah, so that's good. All right, so wonderful to be here, and so I'm going to talk about some work which we've been thinking about for the last 5 years or so, and it involves some many-body physics, classical chaos, as well as entanglement. So hopefully I can convey some bit of that excitement, and this solvable is a bit of an overstatement, as you will see, but we'll see as we go on. So I'm going to motivate the kind of things that are going to follow first, and I'm going to talk more about single body chaos, because a lot of that carries over really, and it'll be good to see where it doesn't carry over. And then I'm going to the central heroes of this are the dual-unitary gates. So I'm going to talk about what they are and the kind of circuits which are made out of them, the many-body circuits which are made out of them. And then I'm going to ask what is the classical versions of these, and that's, if I get the time, I'll come to that. So yeah, first of all, let me remind you of Hamiltonian chaos, which arises basically because some systems do not have enough symmetries. Continuous symmetries which lead to constants of motion or separability. So here is just free particle moving inside these 2D enclosures. It's just reflecting off these boundaries. Here is a circular billiard, and a ball, a single trajectory is shown here. This is not a boundary, it's just a reflection of the dynamics itself, or the caustics which are present here. Here the angular momentum is conserved. In addition to the energy, you have two constants of motion, 2 degrees of freedom, and it's integrable. And similarly here, the individual the energies in the two separable degrees of freedom, x and y, are conserved, and therefore this is also integrable. Elliptic billiard is more interesting. It's not obvious. It doesn't have a rotational symmetry, and it's not separable immediately, but turns out that there is a second constant of motion apart from energy, which is the product of the angular momentum about the two foci. So this is also integral. But almost practically any other shape that one cooks up, it will be non-integrable. So here are some of the classic examples of a square in which a circle has been removed, so that the particle is bouncing off the circle in the interior and a square in the exterior, called the Sinai billiard. It's been shown rigorously mathematically to be fully chaotic in the sense that I will explain. And this is a square in which you have attached semicircles. It looks like a stadium. It's called the stadium billiard, or the Bunimovich billiard. This is a cardioid billiard, which is R equals 1 plus cos theta. That is the polar form of this. In fact, all three of them are proven to be fully chaotic. There's no regular orbit at all, or stable orbits. So these are, in some sense, extreme cases of simple in that sense that these are just one particle systems which show chaos, and what is chaos for us mostly depends on what you're talking, but one of the most important things is sensitive dependence on initial conditions. Two nearby initial conditions in phase space will diverge exponentially if there is chaos, and if there's no chaos, will diverge only polynomially in time. And also mixing. Mixing is a characteristic which can be measured, for example, by correlations, phase space correlations of two functions. Let's say one of them is evolving with the time, and the other is not, and you look at the correlations and how they decay. That's another mixing characteristic of chaos. So, in fact, if I didn't face Murphy's law today, this would be working, but it's not. So this would be an animation of a particle inside this and a particle inside this. There are actually three particles inside this, which are starting from very nearby. You would see this divergence. You must have seen these, some of the double pendulum and so on is very common examples of that. Now, if you were to look at the quantum mechanics of such systems, what does one see? Well, it was thought from the early times that since there is no constant of motion apart from the energy, there's no second integral. If you were to look at an eigenfunction and look at, let's say, its Wigner distribution on a phase space, it's a kind of a phase space representation, it would be microcanonical on the energy shell corresponding to the energy of that eigenstate, essentially uniformly spread. And that will give some implications for eigenfunctions, for example, in real space. Here I've plotted some excited states of the cardioid billiard. This is the modulus psi square in the position space. And you can see that it's actually looking like random waves. In fact, there's a very good model of these which was constructed by Michael Berry, which just says that at every point you consider intersection of random waves. Random in what sense? So the directions are random, but otherwise the momenta of that are just characterized by the energy of the state here. Because the most important difference, even at the classical level, between this integrable billiard and non-integrable is that if you look at an integrable billiard, in terms of the trajectory, at any given point, you will find two trajectories at most, two trajectories crossing each other, whereas in a non-integrable billiard of this kind, at any point you can have infinity of different trajectories, different directions in which the trajectories go. So that's kind of reflected in these waves as in the eigenfunctions as kind of random wave superposition. But this is another state, in fact, just next to it, and you can see that it shows very different characteristics, what people call scarring these days, or actually it's been called scarring from the early days. It's called scarring because it's concentrated on an unstable periodic orbit, because there are no stable periodic orbits in chaos, but there are exponentially large number of unstable periodic orbits. They play a very important role, and they show up in isolated wave functions like this without announcing anything very special. So this is an interesting kind of deviations, and in fact the morphology of states like this are still being studied, especially now in many body contexts. There's many body scars and so on. Yeah.
Is it necessary to be at a high quantum number, or can you see signatures low quantum numbers?
Yes. So as you're getting lower, so the number of nodes here would be decreasing and so on. So the statistics of this would become more less, would be less convincing if you say that something is normal distributed and so on. Your sample size will become smaller. But I would say that unless you are really at the ground state or maybe a first few excited states, you are going to see this effect. It also depends on the Hamiltonian that you're considering. Like in this case, it's clearly homogeneous, so it does not really matter what the energy is. So all the characteristics which you're seeing is actually quite energy independent. But if you had something like a harmonic oscillator plus anharmonicity, it might depend on the energy very much on that. So it depends on that aspect as well. So traditionally, people have looked at things like, look at the eigenvalues of this quantized chaotic systems, and there is no ambiguity here. We know that it's a chaotic system classically. We have quantized it just using Schrodinger equation, solved for the eigenvalues. You've got some eigenvalues, and then you can look at the gaps in these eigenvalues, and you can see that there is a very nice difference between the case of integrable billiards like this, a circle billiard, and the nearest neighbor spacings or the gap spacings would have an exponential distribution like this, e to the minus s, which says that two nearby levels are highly likely to be found. So levels cluster when there is integrability, whereas the opposite happens if there's chaos and you have level repulsion. Levels like to be far apart when there is chaos. In fact, they are much more correlated here. And the interesting observation from 1984 or so was that random matrix theory, which was studied as some many-body nuclear physics kind of model for nuclear resonances, was applicable to something as simple as this. So these are random matrix eigenvalues, and their spacing distribution fits beautifully that of these single chaotic systems in which there is a definite Hamiltonian which is given to you, but nevertheless the fluctuations follow these statistical laws. So this is, in fact, there is a difference. So this is the spectral statistics. So if it's integrable, it's Poisson, as I said here, that is the circle billiard. If there's time reversal symmetry, there is a linear level repulsion, so it's s times e to the minus s square, which is this Gaussian orthogonal ensemble. And if there is time reversal breaking, that's quadratic, that's even more level repulsion if there is breaking of time reversal symmetry. I should also say that if you look at the states themselves, eigenstates, they also have statistical properties. As I said here, there are these random looking states. So if you look at a state in some basis, and the dimension of the basis is, let's say, dimension of the Hilbert space is, let's say, capital N, then if a state is uniformly spread, of course, if it's spread everywhere, you would expect that it's got components everywhere, and this so-called participation ratio is measuring what is the number of significant components. You would think that it is capital N itself, but actually it is 1/3 of this if there is time reversal symmetry, and 1/2 if there's no time reversal symmetry. So typically only 1/3 of the Hilbert space is occupied by a random state if there is time reversal symmetry, or about 1/2. So it's not uniformly spread that way. So you could think about these factors of 3 and 2 as some kind of quantum effects as well. Okay, so there are many solvable models. So these things, yes, we can write them down. They are fairly simple, but for us to understand the details of it is still not that transparent. So mathematicians as physicists have studied very simple models. Yeah, please. Single particles won't really have a Thouless time as such, so it would, or if you scale it with some effective Planck constant anyway, that will go to 0. There is an Ehrenfest time scale, which I will come to, but actually I don't know about Thouless time scale. Thouless, because most of these things would just start from Right. The Thouless time? Yeah. I don't know, but I think in single particle physics, the Thouless time doesn't really play There is another time which is a short time scale, which will tell you a kind of classical quantum correspondence time. But the problem with these kind of form factors which you are talking about is that dynamics is washed out, because it's not a self-averaging quantity. So you need to do some averaging over something. When you're doing that, you're really also blurring out these dynamics which is happening at short times. So, and since there is no length scale otherwise, like number of particles or size of the particles, it gets blurred out. So it will almost, what you're seeing is, there will be this, in more of a many body thing, you will see some decrease and a ramp. Here you'll see only the ramp and more. That's a different, there you're talking about some impurity and so on. Here I'm just talking about a single chaotic system. So like for instance, if you put in the billiard some, scatterer, you're changing the system into something else. I don't know what is the kind of effect of it. Okay, so so this is still classical, and this is a map which is linear. So we have a two-dimensional map. N is now the time here, and so these two-dimensional flows give rise to two-dimensional maps, which are area preserving Poincare surface of section. So people have looked at area preserving maps for a while, and this is the linear map. Nothing can be simpler than this, and without this modulo 1 there's no chaos in it. But because of the modulo 1, if this map is expanding in the sense that its eigenvalues are greater than 1 and less than 1, so the trace of m is greater than 2, there will be an expanding and contracting direction. And if you pull it back with this modulo 1 so that it's living on a unit torus, then it's actually a fully chaotic system which is kind of solvable. So this is an example of a solvable fully chaotic system, where all the I'm still talking classical, so where all the periodic orbits are, there are a dense set of periodic orbits, all the stabilities, all the Lyapunov exponents and so on. And in fact, you can see, this Arnold cat map is in particular one of these examples with the 1, 1, 1, 2. And you can see for this that it's isomorphic to stochastic processes. So statistically, classically, they are isomorphic to finite Markov processes. In this case, it's a subshift on 3 symbols. So it looks like a Markov process with 3 sites. And so this is what would happen. This is an example of a mixing system as well. So if you put some density here, like the picture of Rajnikant, and then iterate this, so this is being stretched along this direction, compressed along this direction, and then it's being repeated, the same image. It's, by the way, an invertible image. So you can get, after a few iterations, 5 iterations, it's here, but the entire information is still here, it's just scrambled. So you can go back, for example, into this. So if I could play the animation, you would see this dynamically, but this is something which is pretty standard. But what I want to emphasize is that there are simple solvable models of chaos in which you know everything. Chaos does not imply that you can't solve for something. And there is an ergodic hierarchy classically, where ergodic systems, where the phase space, let's say roughly phase space average is equal to some time average, they are at the bottom of the hierarchy. Ergodic does not imply that it's mixing. Ergodic simply means that you have a trajectory which would go to every part of phase space, but if you have some density, it doesn't mean that that will mix. So that's the mixing systems higher up on the hierarchy. And then there is Kolmogorov systems, and this is an example of a Kolmogorov system in which it's not only mixing, but it's also mixing in some sense, it's mixing exponentially fast. So this is, you might think about this as exponentially fast mixing, whereas a mixing system can also be polynomially fast mixing, although that's rare. So most of the systems are exponentially, if they are mixing, they are exponentially mixing. At least there's low dimensional chaotic systems. And then at the apex of the hierarchy are these Bernoulli systems, where again correlation functions decay, but they decay. There are significant correlation functions, which means that there are densities which are generic densities of some kind, in which the correlation functions decay instantly. So that means that as a statistical process, it is as random as a coin toss or independent random processes. So you could think about it like as random as a coin toss. There is a one-to-one correspondence between orbits of a deterministic dynamical system and a stochastic process. So that's a classical ergodic hierarchy. Such a clean ergodic hierarchy is kind of missing in the quantum case, and we will see some examples where perhaps such an hierarchy can be constructed. Oh, yeah. Because instead of Rajnikant, Arnold put a cat on there. You can put your favorite figure. So Arnold and Abbes have this book called Ergodic Problems of Classical Mechanics. It's a lovely small book. So that's where this first appeared, 1967. They drew a picture of a cat and saw what happens to this. Yeah, so in physics, cats are regularly subjected to various kinds of tortures. So this is that. All right, so these kind of cat maps, they're not that generic. Yes, you can solve them. So for generic kind of systems, let's look at a generic area preserving maps. So these can be constructed from kind of Floquet operators such as these. You have some Hamiltonian, H0, can be any structure, and maybe it is being added by or kicked by this potential V, and this is a kick which is periodic in time. So this is a time periodic Hamiltonian in which the kicking is periodic. The fact that it is kicking enables us to write down things analytically. These kind of maps can be constructed explicitly. For example, a wide class of problems that have been studied or of relevance, this H0 has a standard form of kinetic energy, and this V is some potential energy of this kind. And then the classical map, which is the position and momentum after each kick. So that's a stroboscopic map, is given by this. So it's essentially like position at time n plus 1 is position plus momentum at time n. Momentum n plus 1 is updated as momentum minus the force. So the impulse here at time n plus 1. So very simple. You can iterate this two-dimensional map, and you can also. So one of the very popular potentials is this cosine potential, in which case people call this a kicked rotor or a kicked pendulum. So this is kind of a, yeah. So we will use this. So with this single parameter k here, and we'll set this time t to be 1, and then you will get a map of this kind, and position and momentum. This position is like an angle now, so it's going from 0 to 1. I've already put a 2 pi there, and momentum can also be actually periodicized without any harm here, because of it commutes with a translation of momentum by 1. So you can put the whole thing on a torus again and study. So that when k is 0, there's no kicking at all, it's free particles. So this is like constant angular momentum or constant momentum. So each color is a different orbit. Okay, so you have many orbits which are plotted here. Momentum is not changing at all, so it's an integrable case here. And then when k is 1, there is this kicking is non-trivial, and you have this transition into chaos which follows the classical Kolmogorov, Arnold-Moser kind of scenario, where rational numbers in which this momentum is irrational, they kind of remain for perturbations, and rational ones break up into these resonances or this exact stable periodic orbits. So you have this family hierarchy of phase space orbits here. There is chaos, a little bit of chaos, which is formed around this unstable periodic orbit, and then there is this period 2 orbit which is stable, and then there's period 2 unstable, period 3, etc. And then there's chaos here. This is an example of a mixed phase space in which both chaos and regularity are both there at the same time. And then as we increase this value of the parameter, almost all orbits are becoming unstable, and a single orbit here will explore this entire region except this island which is surviving around here, because the fixed point here has just lost stability at k equal to 4. And then beyond that, even this has lost stability at k equal to 9, for example. A single orbit, that's why you see only one color here. This is one orbit which is going all over this place in this manner. But I must emphasize that at this point it's chaotic, it has an infinite set of dense set of periodic orbits, etc. And these can be quantized very easily because they are in the standard form of Hamiltonians, and so this quantum map is just, you have basically free motion here, exponential of p squared, and then there is this kicking, so it's a product of these two cosine 2 pi q. And the nice thing about this is that you can continue using a torus phase space picture, and because position and momentum are both periodic, both in the quantization, both position and momentum take discrete set of values rather than continuous, and you have a dimension of a Hilbert space which is finite, so it's a nice playground for finite quantum mechanics, and this n is related to the Planck constant or scale Planck constant by 1 over n. The 1 is the area of this, so this is really dimensionless Planck constant, and as n goes to infinity, this goes to the classical limit. So one can study the quantum versions of this kind of system and see what happens, and people have done this. Unfortunately, I'm not going to be able to show you any of these nice animations, and they are quite nice actually, but I think I'm completely out of this. So I can't show you this. So, but let me just tell you what those pictures are going to do. In the first case, k equal to 0, I'm going to start in this integrable case with some density of points classically, and it's just going to be evolving with constant momentum around this. Quantum mechanically, it's still going to be, there is a wave packet which I'm going to put there, it's going to move like classically. Because of the periodic boundary conditions, there's interference, and there can be revivals and so on at longer time scales. But you will see a classical quantum correspondence break down at a time scale of about square root of n, which is about 1 over square root of h bar. And k equal to 2 is a case where there is a mixed phase space, like I don't have k equal to 2, but it's somewhat like this, let's say, and then you still have a large classical quantum correspondence, whereas k equal to 9 is a case when it's fully chaotic, and then the wave function almost immediately spreads out into this, but there is still a quantum classical correspondence time which actually goes as a log of n or log of 1 over h. So you can see that between an integrable and a chaotic system, these time scales are very, very different. So an integrable system has a much longer classical quantum correspondence time, whereas a chaotic system has a much shorter one. Therefore, if you want to see quantum effects fast, a chaotic system does that for you, and it's actually a very fast time scale. So there have been arguments from people like Zurek that there are satellites of large planets which are shown to be chaotic just from observational data, and they have been around for so long that by now they have well passed their infest time scale, and we should be seeing quantum effects if we are going by this. So there are other additional decoherence effects and so on to take into consideration. Okay, so this is actually the Ehrenfest time scale, Milan. This is the short time scale which is present, which may be, compromised or changed if you have some other kind of diffusive processes. Okay, so going to many body systems, there is a whole host of things which carry over. For example, people do things like nearest neighbor spacing statistics, and there also you see, when you have some many body physics, you can still see Poisson versus Wigner. In fact, there is no classical limit in these cases, and mostly these are taken to be the signatures of chaos. And there could be other things like entanglement growth and fast and slow growth, which might indicate some kind of ergodic phases or localization and so on. People have also found low entanglement states which have been called scars, and you can identify them with some special set of states in a sea of ergodic looking states. So people have also found these kind of things, although its connections with any kind of periodic orbit, whether it's stable or not, that kind of thing is missing most of the time. And then there are other interesting phenomena like discrete time crystals and so on, which people have found in these kind of many-body quantum chaos. And in fact, there's this interesting study by these people, Alex Altlin, David Vincenzo, who looked at transmon arrays, which are interacting Josephson junctions, which are essentially like a cosine potential, so the kind of pendulums which I showed you, but without any time dependence. And they are interacting even without an algorithm running on it. And they are two-level systems ideally, but actually there are other excitations, of course. And what they found is that this can operate very much at the edge of chaos. So this is these are two-level systems, but actually you can find excitations to higher manifolds of 5 individual transmon levels, and the collective many-body system can actually excite into a very quantum chaotic kind of states here. And this is all the energy levels as a function of some detuning parameters, and you see the kind of things that one sees in a quantum chaotic systems. I didn't show you energy levels, but basically they are dominated by some kind of level repulsions, which are also seen in the Wigner statistics when I said that in chaos there will be a repulsion of levels. So when you go to many-body physics and look at these kind of quantum, you have to watch out for when there's a localization or delocalization, which might then affect the performance of the computer. I believe in this case, for instance, detuning and disorder is necessary, but at the same time you need to also ensure that it's not it doesn't go into some phase like this. Okay, so this is another quantum computing example where you have this famous experiment from Google, and there's more recent experiments, but this is from 2019. You have an array of qubits which are given by these crosses, and then there are these interactions between them, and or these gates which are connecting the two qubits. And you can see here there are 5. So in this particular thing, there are these 5 qubits, and these 5 crosses are here. And like for instance, in this first level here, this green A is connecting these two. So the other single qubit gates are as they are. These two are interacting with each other, and in the next layer, you have these 2 qubits which are interacting, and so on. And you can apply a different sets of gates to each of these at each of these layers, and then ask after a bunch of layers, what is the state of this system when you initialize this, let's say, in a state which is all 0. So it's an example of something like a time evolving system where you have a circuit consisting of single qubit gates and 2 qubit gates, and it looks that these have been studied as random quantum circuits, but what is the statistics? When you measure, you will get some sequence of ups and downs. Let's say that you are measuring it in the Z basis, the standard basis. You get some strings, and then you keep doing it again, and you will get a distribution of outcomes. And the question is to sample over that distribution, find out what is that distribution sampled over. If you do it classically, this has about 50 qubits in it, so it's going to take a very long time. So that was the argument that actually one could do this much faster if you had a quantum computer like what they did. So classical simulation of distribution of measurement outcomes is hard. It's not been rigorously proved, but there's a lot of support for something like that. And in fact, the outcomes here, by the way, are, if this is chaotic, they were expecting to see this exponential distribution, which would be for a random state. Like I mentioned, that the participation ratio there goes as n by 2. Although there's no time reversal breaking here, because it's a time evolving state, it's typically complex, and therefore you expect it to be n by 2. And therefore this is called a Porter-Thomas, and this factor 2 is very important in this calculation. And yes, so whether you're getting a random state out of this, in that sense that I talked about in this integrable, non-integrable billiard, is again yet to be rigorously established. This probably is one of the kind of open problems, in the sense of how much of many-body non-integrable systems with short-range interactions and so on, finite rank interaction, will behave like a random state. Yeah, so this is so I'm going to talk about circuits of this kind. Yeah, number of qubits, total number of qubits. Not the depth, like for instance in this case, right? If you have initialized in this, it would be just 5, which is come. No, the circuit depth is actually contributing to this. So if you do this very early on, you will certainly not find this. So you have to wait for some time till it is getting randomized. See, there is no classical limit as such in this, but in fact there is some kind of a connection, in the sense that I said here that this Ehrenfest time is scaling as log of n. So you have such a scaling for you to wait. I mean, the depth which you are having to wait for scales as that kind of. If you have that many qubits, you'll have to wait for. I mean, the dimension of the Hilbert space, rather. So there is a fair bit of work on what is, if you assume that things are random, right? I mean, random 2-qubit gates are being applied. There is a fair amount of understanding of how long you need to wait before you thermalize. Again, it's a question of what do you mean by thermalization. So there is a whole thing about designs where you say that I'm going to approach a completely random state up to some order, some polynomial order, and then that up to what time you are, I mean, if you want some order 2, you wait shorter times, and then so on and so forth. There is a fair bit of work on that, and it continues how to make good designs using random gates. But in fact, I think some of the interesting things I'll probably mention that is that probably random gates, if you just pick at random, is not the best thing for one to do, and one can do better than that. Yeah. Distribution is over measurements. You've done a lot of measurements and you're seeing the outcome. Yeah. Yeah, so you're saying how do I sample these things? Yeah. Not necessary. I mean, you just prepare again and you run through the same set of gates. Yeah, they're just unitaries which are there. You pick them at random, but you can do the same experiment with the same set of random gates several times over. Okay, so let me come to the main part of my talk about brick wall dual unitary circuits. So are there non-integrable quantum circuits that are in some sense also exactly solvable? These things may not be exactly solvable, although there's some arguments which one can do from a random matrix point of view. So there are these papers by the Gour group and Prof group 2016 and 2019. So one of them reads particle time duality in the kicked Ising spin chain. Other is exact correlation functions of dual unitary lattice models, which kind of, I'm going to talk about those ideas here. And the idea there is that instead of having a random circuit of this kind, you can do as well random circuits of that, but it's good enough to consider a Floquet system, which means that you're repeating the same layers at all times. So a Floquet system built on two-site unitaries. So these are the bricks, and these are the local space as dimension d. It could be a qubit if d is 2, or anything else, it doesn't matter. And so these are these unitaries and the two particles. You can represent these unitaries in this pictorial manner. This is J and beta, two particles or two sites. And think about the vertical as time, because this output is I alpha, and this is representing the gate U. U dagger is just different color. So the model is that of a depth 2 brickwork circuit on a 1D chain. So it's basically just 1D chain, spatial 1D chain. One time step applies two-side gates U on even and odd bonds. So here you go. So here are even and odd bonds. So you apply this 2 qubit gates here, and then in the next half layer you apply it on the other alternating bonds, so even and odd, so that everything is interacting at the end of this one step. So, and then you repeat this. So your dynamics is, or your time evolution is this big operator U, which is composed of these small two-site operators to the power of t. And we want to know what are the kind of dynamical properties of such a system. So this is the model. And now this U, the critical aspect is just this 2 brick unitaries U. So let us look at that. So they are unitary. So it is U adjoint as identity, which has this, that's what this means in component form. Pictorially, so if U dagger is this, so U dagger identity, and this is there's a contraction of these is equal to identity. So that is elementary kind of tensor network picture. A dual unitarity is when there's a space-time rotated gate is also unitary. And what is this quote-unquote space-time rotated gate? It's defined in terms of this original gate in the following manner. So you are ij component alpha beta is I alpha j beta. That is, you're interchanging the components of alpha and beta. See, this Greek and Latin indices are interchanged, so you have all the Latin on one side and all the Greek on the other. It is basically a permutation of this unitary matrix, which is some rearrangement of its matrix elements, but you require that that also be unitary. So it's a very special kind of a unitary operator. And in terms of pictures, this is how it looks. So you have these two as the sites, and this is now time, and you are contracting it in the sideways. So this is all system 1. You are contracting both the different times, if you look at this as the input and output, on one side. And this should also be identity. Okay, so this is a sideways contraction, and that is called space-time because you're thinking about this as space and this as time, and so there are some transfer operators on both the space and time directions. You require them to be unitary in both the space and time direction. But this is the basic definition of that. So if you take 2 qubit gates, for example, they are dual unitaries of 2 qubit gates are all parameterized by a single parameter apart from these single site unitaries, single qubit unitaries. So they are all of this form. So U1, U2 are 1 qubit, V1, V2 are arbitrary 1 qubit. The 2 qubit gate is given by this exponential pi by 4, and there is this J which is here. So this very simple matrix. This is the Cartan form, Cartan decomposition of 2 qubit gates, and it's important that both of these are pi by 4, and this is the free parameter J. So such matrices exist, such operators rather exist in all dimensions, and they are well understood for qubits. They are less well understood for other dimensions. So how can we make use of this? A kind of contraction was shown in this paper of Prosin. So here we want to calculate such a correlation function, which is a correlation function between an observable localized at y and localized at x, single particle correlations here. So you want to evaluate something like this. Yeah. Sigma j is conserved in what? Yeah. 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 Not necessary. You have all of these things will spoil all of that. Single qubit gates can be random, can be anything. Yeah. So yes. So for such a thing, so this is, so you read this picture like this. So this is equal to this. So now all the red gates are u to the power of t. In my earlier slides it was adjoint. So you apply u to the power of t here, and then there is this gate which is ay, this observable or this operator here, and then you have u adjoint, and then you have to contract it with this operator at x. Now you observe that there are these combinations here, which you can apply just unitarity condition like this and simplify this. So it's rather simple in one step to use all of them, and then you can reduce this to this. So you already see that you have this kind of a cone structure, and there won't be any correlations outside of this so-called light cone. And now you have this observable inside the light cone and the correlation within the light cone. You can't do much at this level if you have a general operator. But because of the dual unitarity and sidewise contraction, you can start contracting from here on the side. And then you start simplifying from that. In fact, that's the idea. And then you continue using the sidewise contraction or dual unitarity. So that means that you have used unitarity and you have created this cone. If you use dual unitarity, you will create another cone where you are actually getting rid of this also. So all of this will become 0, and this correlation becomes 0 because this is nothing but the trace of this just circle here is the trace of this observable. And I didn't say that, but this correlation function, it will be a correlation function if we assume that these are traceless operators. Otherwise you can subtract the trace and create a real correlation. Create a correlation matrix. So we'll assume that they are traceless without laws of generality. So this will become 0. So this correlation is 0. And similarly, if your observable is right at the corner, but not exactly on this side, observe that this one is on the left leg here. This one is here. Even in one step, this will become a trace of this using dual unitarity, and this will become also 0. So the only correlation which is non-zero, as observed by them, was that if these observables are exactly on the light cone, then it's non-zero, and it can be calculated because of this recursive structure. It can be calculated as just a power of a single operator, and that operator is this channel which is given like this. So in this sense it is solvable. Look at this channel operator. So this is the two-site operator u, and this is a single-site operator sigma, and you're tracing out on the site in which the sigma is, not on the environment side if you wish, but this is still a channel. This is an object which will take you from the single operator to another single operator. So this is a channel, and in terms of a picture that is given like this. So it is this object which is determining the many-body correlation, and this channel can be written in terms of the two-side unitary in this manner here, where this u gamma is a partial transpose operation on this u. So the partial transpose is just you interchange the Greek alone or the Latin alone. So here is a transpose only on one of the subsystems. Here I have interchanged the Greek. And then this R is the realignment which I introduced before. So the operator or this channel can be written down explicitly, and the spectrum of this matrix, which is just a d square by d square matrix, determines the correlations of the full circuit of observables on this light cone. And there's been a simulation of this with a 91 qubit machine from last year, where they did this simulation and this is the kind of dual unitary which they used was based on qubits and based on the kicked Ising model. So in fact this dual unitary consists of this interaction element which is essentially like a sigma x interaction here, and then there are these single qubit gates in between these two interaction steps. So this makes the whole thing actually a 2 qubit gate, and with the appropriate choice of these parameters here, they can make this actually a dual unitary operator. And then they found this correlation numerically, experimentally, and they found that the correlation mostly lived on the light cone and was very faint in the inside of this. So they are testing many of their algorithms for, to see if they can do the corrections, because this is what they get without error mitigation, and with error mitigation they get something which is quite different, but in line with what is expected of these circuits. Perhaps why this may be interesting is that these dual unitary circuits create a lot of entanglement. And let me say that these correlations, they are non-zero only on the light cone, not inside, but it doesn't mean that there is actually a very non-trivial scrambled phase inside this, which is creating this zero correlation inside the light cone. Okay, so now we can look at these channels, these d square by d square matrices, and construct some kind of mixing rates out of them. So there's one eigenvalue which is 1 always, which just comes from the fact that it's a completely positive trace preserving operator, which is unital in this case. So this is kind of a trivial state. So the non-trivial states have eigenvalues which are smaller than 1, and the correlation function on the light cone is decaying like this. So the mixing rate obviously depends upon the largest non-trivial eigenvalue, modulus of the eigenvalue. And these are kind of dynamical classes for qubits, non-interacting if all the eigenvalues are 1, non-ergodic if some of the eigenvalues are 1, so some of the constant functions can survive. Ergodic and non-mixing if there is no eigenvalue 1, but some of the eigenvalues are modulus 1. So it lies on the unit circle, so the time average correlators vanish. So this is another definition of ergodic. Ergodic is the phase space average being equal to the time average, but from the point of view of correlation, if a time average, infinite time average correlation vanishes, that's ergodic as well. Ergodic and mixing is all non-trivial eigenvalues are smaller than 1, and that is the exponential edge decay on the light cone. And what is the effect of local unitaries, these single qubit unitaries, on these channels and mixing? So if you have this 2-qubit unitary U and you have the single site unitary, which may be like a local field or something, then the channel which is dictating how the circuit is decorrelating is connected to the channel of U by this unitaries on both sides. So it's not as if the eigenvalues and mixing rate don't depend on the local unitaries. They do depend, but there has to be a crucial role which is played by the non-local part of the 2-qubit unitaries. So I want to look at that more closely, but maybe I should also pay attention to the time. I think I have only 10 minutes, is that?
Yes.
So I'm pretty much close to my introduction, end of that. So we're in a happy state. Okay. So maybe I should actually I wanted to say a bit about these 2-qubit unitaries themselves, which are making up the circuit, because when do you expect a many particle circuit to become random or scrambling? It would definitely depend on the properties of the bricks which are constructing that. So especially if they are very entangling in some sense, then that you should expect. So in fact, maybe I'll cut through this and just say that dual unitaries have maximum operator entanglement. You can take an operator U, treat it like a state, and look at its Schmidt decomposition and its entropy, and you find that in fact for dual unitaries, all dual unitaries have maximum operator entanglement. So they are in some sense the Bell states of operators. But that's not the whole story. Because there's another interesting quantity called the entangling power of 2-qubit gates, which tells you on the average how much entanglement is created by that when it's acting on product states. You take an average over all product states of some entanglement quantity here. For us, this will be a linear entropy, so 1 minus trace rho square, where rho is the reduced density matrix. And then you can have a measure of how much entanglement can be actually created by that unitary operator. And it turns out that this is nicely connected to the operator entanglement. This was derived by Zanardi here some time ago, that the entangling power can be written in terms of operator entanglement of U plus operator entanglement of U times the swap operator, which is interchanging two systems. And this is an expression, simple expression like this, if this is a linear entropy. And we also found it useful to define another quantity called gate typicality, where we are just interchanging some signs here. There's a minus and a plus which differs from this. And these ranges of these entangling power and gate typicality lie between 0 and 1. And these local gates have both of them to be 0. Local gates meaning just product of local unitary gates or identity. And a swap operator has entangling power 0, clearly it doesn't create any entanglement. If you act with a swap operator, it just interchanges two states. So it acts on a product, it remains a product. But the gate typicality is large, it's the largest possible. So the gate typicality is some kind of measure of non-locality of the gates. The operator entanglement is maximum, which is the entangling power of the swap, if and only if the operator UR, the realignment is unitary, that is it's dual, and this EUS, which is the swap, is maximum if and only if the partial transpose is unitary. So given a bipartite unitary, these two objects are very important, the realignment and the partial transpose. And this entangling power will be 1 if and only if this matrix U is unitary, the gate is unitary, realignment is unitary, as well as its partial transpose is unitary. So if all of them are unitary, you would call such an object a 2-unitary or also a perfect tensor in some literature. So let's look at, for qubits, 2-qubit gates, how does this entangling power versus gate typicality look? So all the 2-qubit gates are here, and you see that there is all the unitary, dual unitary gates are here. Between swap and what is called DC naught, all of them are on this line here, and this is local here, 0 entangling power, and this is the C naught gate, this is the T dual or gamma dual gates, which are such that the partial transpose is unitary, and they don't meet for qubits. So qubits don't have entangling power 1. They don't maximize the entangling power. There are no 2 qubit gates that maximize the possible entangling power, whereas for 2 qubit gates, that is for d equals 3, there are such gates which maximize this. And this curve here is powers of swap, fractional powers of swap. So in fact, this is just to emphasize that for highly entangling gates, for qubits, there is nothing here. This whole dual and T-dual lines don't cross, whereas for qubits they do. So this is a kind of plot which we produced after a lot of effort, but this is something which is not proved yet, that there is a gap here. Whereas if you go to D is 4, there is no gap, and this is a fully fledged region here. You can find out more about these in this paper which we wrote recently. It's a review actually of very seemingly different topic of absolutely maximally entangled states. Okay, so there are numerical algorithms to find dual unitaries beyond D equal to 2, and a swap times a dual unitary, T dual unitary is dual unitary. So swap and T dual here, they are kind of, T dual and dual unitaries, they are kind of related by the swap operator. And diagonal unitaries are simple examples of T dual. So you can always construct dual unitaries in any dimension. Okay, so maybe I have basically time to probably discuss this picture here, where what we are doing is going to qubits here, because there is a difference between qubits and qubits. And what we are seeing here is the eigenvalues of that channel M, which is determining the mixing rates of circuits made out of them. And we are taking a gate with which we are fixing that non-local gate to have an entangling power which is small, 0.09. It can go from 0 to 1, so this is small. And this is the largest eigenvalue as we are varying the local gates. So you see that there's not much of a variation. It lies on the circle, and the smallest eigenvalue is also plotted here. And there is a curve here, a circle, which is a square root of 1 minus entangling power, which is also plotted. And this is for a larger entangling power. You will see that the eigenvalues are getting inside the circle, the blue part of it, and that's more clearer here as we increase the entangling power more and more. So the eigenvalues are getting smaller, the mixing rates are getting larger, and what is interesting is that there is this curve which is square root of 1 minus EP of u, which seems to find out for you what is the largest eigenvalue which determines the mixing rate. So indeed this entangling power, this is an average over the locals. So we proved this in this paper, that you can average out over the local unitaries, and then what you have is something which is independent of local unitaries. It depends only on the entangling power of the 2 qubit gates, like this. We realized later this is actually consistent with a single ring theorem of random matrix theory. You can see these rings. Well, you're not seeing a single ring. If I plotted all the eigenvalues, you will see a single ring here. And the outer radius of this single ring theorem, which by the way, Manjunath and IISc was responsible for proving this, is consistent with this. So there is some interesting random matrix theory also behind this. But what I want to probably emphasize here is this phase diagram for dual unitary circuits. So for qubits, the maximum entangling power is not 1, it's only 2 by 3. And you can make it mixing, but you can also make it non-mixing in the dual unitary line. This goes from swap to DC naught. This is the maximum on this. But if you go beyond qubits to qubits, you find that there is a point where this is 2 unitary, entangling power is 1, and this eigenvalue is strictly 0, not the average. It's actually strictly 0, and you have all the eigenvalues to be 0 except the trivial eigenvalue 1, in which case the correlations are instantly decaying, and therefore we call them Bernoulli, because if you recall the ergodic hierarchy of classical mechanics, this is like an IID random process or a coin toss in which there is no correlation at all, and this is like that. So we call this Bernoulli, which is constructed out of two unitary or perfect tensors. Yeah, so quantum Bernoulli circuits are in some sense the apex of the hierarchy. There is ergodic, mixing, and Bernoulli. Bernoulli circuits are such that the brick, the gates which are making it, have maximum possible entangling power 1. It's possible only beyond qubits. So this is U is 2 unitary or a perfect tensor. All the eigenvalues are 0 except the non-trivial one. And we proved that not only the single side correlators vanish, but also two side correlators instantly vanish in any space-time separated point, even on the light cone. Okay, so we can find families realizing these. How do we find if there are such operators? There are, and we have in this as well as in this other paper many ways of constructing this. I introduced the cat map, Arnold cat map. There is a quantization of the Arnold cat map, and you can construct coupled Arnold cat maps which are dual unitary for all local dimension d, and they will be 2 unitary for odd dimensions, and they can also be used to construct such Bernoulli circuits. Okay, so I'll stop here. I won't have time to go into classical analogs, but I just want to say that actually this is not some unique quantum phenomenon. In fact, you can construct dual classical circuits, and I showed you the standard maps. You can construct kind of dual coupled standard maps such that you can solve a many body coupled standard map for correlations, again in terms of some kind of transfer matrix or this kind of a channel, but it's now entirely classical, and these classical channels have these kind of eigenvalues which are determining these decay of correlations or these Ruel-Polycott resonances. And it now depends quite interestingly on the kind of single particle or single or these standard maps which are constructing this many body classical system. And one can also do comparisons between quantum and classical channels. I will not go into the details. I'll probably just stop here by saying that yeah, so I'll probably stop there. I'm already over time. Thank you for it. Yeah, sorry about that scrambling operation in the end. Unfortunately, the animation is not working, but you can't see Rajnikant in action because he survives the cat map. So, yeah, it's some way away. But please tell me, ask me the question. Yeah. Right, because it's unitary dynamics. Sure. No, the information is different, but it is conserved in the sense that you can get back the picture without any distortion. For instance, if we do this, along with this, if there is some noise, there is some blurring, right? Then information is lost. Then you can't recover this picture, or you'll get only an approximation of this. So that's what it means. You could think about it like that. Yeah. Yeah. Right. Correct. Yeah. Right. This one, right? right? Yeah, you do that, yeah. Yes, yes. Yes, yeah, yeah. Okay. It's exactly what you're saying actually. I didn't write down a Hamiltonian. For example, all this kicked Ising model and so on. It's just a normal Ising model with nearest neighbor interactions and on-site potential. You can write it like this. So this is not something unusual as you're saying. It's actually rather standard. Yeah, exactly. It's coming from, you can think about it as a trotterization of a continuous time, or you can think about it as a Floquet operator of some, time periodic system, or you can think about it as a trotterization, in which case you have a trotterization time scale which you have to worry about. But the structure is nothing unusual, and people have studied other structures. So this brick wall structure, so the most important thing is this picture here. Everything has unitarity. If this is also there in the gate, then all this magic follows in terms of your being able to find these correlations analytically and so on. Otherwise, there is nothing special about this model. For example, they have done, in fact, the Ising model. The Ising model is not solvable if you have both a longitudinal and a transverse model, transverse fields. So in this case, you have both. So it's a non-integrable system. Maybe I should have emphasized that. These are all non-integrable. And in this case also, because you have a longitudinal field, it's non-integrable. All the Jordan-Wigner magic won't work here. But yeah, you can write this exactly in this form. Yeah, exactly. That is what is. Yes, exactly. So that's why you need some particular magnetic fields at which things will work. For example, in this one, there is some pi/4 and so on, which is important phase. So it's also, there is this entire literature on the Clifford gates, and those are also solvable in this sense, but they are not necessarily dual unitary. So dual unitaries are a broader set of gates than that. Yeah. 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 And by the way, yeah, I didn't emphasize, but this transition happens only, there is this critical entangling power for which the qubits is actually the critical entangling power is a maximum. But sorry, what was your question? Entangling power is kind of our control parameter. So good question. Yeah, actually there's not much known about time evolved states. There are some particular initial states which people have studied, some matrix product states or some things which can be solvable. A little bit of OTOC work, but these things remain to be done. It would be interesting to do, to see the kind of, just in terms of time evolution, what kind of difference is arising here. Definitely we expect to see something fairly unusual or spectacular when EP is 1. Unfortunately, these things are not that easy to do experimentally, I believe. I should also say that there is essentially only one unitary operator here, which is Bernoulli for qubits. So that is that, yeah. Yeah, but a lot needs to be done. That's what I'm told, yeah, because you'll have to implement this many qubit in a qubit architecture, which is suited for a qubit architecture. But it would be good to do that because it is qualitatively different. Yeah. Thank you. Thank you for the invitation again.